We're going to spend a lot of time for the rest of the semester discussing carbonyl chemistry. Remember, carbonyl is a C-double-O bond. So we got to start by being able to name aldehydes and ketones. Remember that an aldehyde is a C-double-O bond at the end of a chain versus a ketone is within the chain. So these are aldehydes. We just name the main chain, remove the E, and replace it with an al, Al. So this we do start numbering, I'm sorry, with the carbon that's in the carbonyl here. So this becomes 3-methyl-butanal. It's understood that the aldehyde is at 0.1. This would be 3-methyl-2-pentanal. And what that's actually saying is that this is an EN. And my apologies, which should this be? It is not a cis or a trans. It is an E. Okay. This would be benzaldehyde. We've already seen that name before. And this would be cyclohexane carbaldehyde. Sorry, I didn't choose that name myself. That's a little bit more difficult there. With ketones, we take off the E and put on the term "-one". We want to give the C-double-O bond as low of a possible identity as possible. So this becomes 3-methyl-2-butanone. In other words, the methyl does not take the 2. This takes the 2. So 1,2. 2-pentanone, cyclohexanone. Okay. We've already seen several ways to prepare C-double-O bonds. So we can start with alcohols and use PCC if it's a terminal alcohol. If it's an internal alcohol, so a secondary, we can use PCC or Na2Cr2O7 and acid. We can take a double bond and splice it through ozonolysis using O3, excuse me. We can make an aldehyde from BH3 and THF with a terminal alkyne. You could also make ketone with H2SO4, HgSO4, and water. And we know how to do an acylation. We just did those within phenyl groups. So one of the first things I want to make sure everybody knows, carbonyls are flat, okay? They have an sp2 carbon, which means that you can have a nucleophile approach from the bottom, but there's not really any one way or the other, okay? There is a definite polarity here to that C-double-O bond. Keep in mind, you could even draw a resonance structure like this. So that positive charge should be on that carbon, partial negative charge up here. There's a directionality here. So nucleophiles are going to naturally be attracted to that carbon. Some of them will actually attack because they're strong enough. Others need a little bit of help. And so there's basic mechanisms to consider here. You can have a neutral or basic condition with a nucleophile, depending on, again, how strong it is. And it will actually attack that carbon, and electrons go up. Then oftentimes it will find a proton source. It can be water, it can be ethanol, it can be whatever the proton source may be. They'll end up giving you an alcohol. You can also do this through acidic conditions where the oxygen comes and grabs a hydrogen first and then the conjugate base leaves. This conjugate base could be the nucleophile, or you could have another nucleophile depending on what you're dealing with here. And then that comes in, kicks these electrons up, giving you the alcohol. Okay. Hydration reactions happen sometimes. They more often happen with formaldehyde because that's what's going to stick more than anything. But this can happen with a base or an acid, just to give you this type of guy. And what happens with the base is just what we saw there. Actually, this is a very good example of these reactions. So here we go. That goes there. Electrons go up, comes and grabs a hydrogen from water, and there we go. Another version of that would be that this guy comes and grabs a hydrogen from an acid. Water comes in, kicks in here, electrons go up, and then water has to come back and remove a proton so that there's no charge on that molecule. In a similar fashion, we have acetals and hemiacetals that can be formed through the addition of water, and we do tend to do this through acidic conditions. So here's what happens, and you'll notice that this line is very similar to what we just saw. If not, there's an R group difference. So this comes and grabs the hydrogen, electrons go back to the base, or the conjugate base. This alcohol comes in here, electrons go up, and then that conjugate base comes and strips off the hydrogen. So you get the what's called a hemiacetal. It's half in between. Okay. These electrons will come and grab that hydrogen, electrons go back to the base, and then we have a switcheroo here. So these electrons come in, that leaves. Do you see how this mirrors what you just had up here? So that means that this is now, it doesn't take much for a nucleophile to come in here and electrons go up. The conjugate base comes and removes that hydrogen, and that's how you end up with this acetal. Now, the coolest thing that we use with acetals is that we use the fact that this is in equilibrium throughout the entire thing, because we can either put this on or take this off. So we can use that as a great protection group. Specifically of the carbonyls, so for example, we use ethylene glycol for this most often. So this is going to end up giving you this weird 5-membered ring here. So this is kind of one side of the alcohol, and this is the other alcohol, if you want to consider it that way. And that's where you get the two alcohols. So this is both an R and another R, it's just that they're connected to each other, right? And so we can put this on, and it will selectively go to the carbonyl right here. And then we can reduce something that's harder to reduce than the C-double-O bond, with lithium and aluminum hydride, something like an ester. And then when we acidify this guy, this will come off at the same time. So that's pretty awesome when you're trying to get something that is more reactive to be protected. Okay. Now finally, I love this subject. I've been doing a lot of research in this area for a little bit. So hint, I love this one, okay? You might see it. Just kidding. But yeah, you might see it. So in this case, we're going to make an imine. And imines just sound cool because they're imines. But basically what this is doing is it's taking a C-double-O bond and making a C-double-N bond. So this starts a different way. I just want to point that out. Your nitrogen is the nucleophile that attacks first. Notice this is in equilibrium. You have to actually have a good pH for this to work. So I say you add trace acid because you don't add a huge amount of acid. Like a drop or two of sulfuric acid might work, depending on what your reaction scale is, of course. So when these electrons come up, I want you to keep in mind, you're in acidic conditions. So if you're in an acid, it's kind of okay for a positive charge to hang around, but it's not okay for an O- to hang around. So once you generate that O-, that's what's going to react with the hydrogen, and electrons go back to the base. Then the base will come back over, or conjugate base, will come back over and grab that hydrogen. Okay. Now, this might look somewhat stable, but it keeps going. This guy will come and grab that hydrogen, electrons go back. And then we have another switcheroo again, just like we saw in the last one. Electrons go in from the nitrogen, and the water gets kicked out. The conjugate base then comes back, grabs that hydrogen, electrons go back to the nitrogen, and you form the imine. So, something I want you to check when you're done here. Did you start with a full HB, and did you end up regenerating it? Because it's a catalyst, you should regenerate that, okay? Enamines are very similar. The difference is what they produce. And that is, instead of having a double bond to this nitrogen, there's a double bond on a bond right next to that nitrogen. So I'm sorry, I wrote this out. There is a carbon right here, okay? So this is almost identical until this very last stage to what we just saw up here, okay? So, electrons go in, these fly up. Come and grab the hydrogen, conjugate base leaves, which then comes and grabs the hydrogen here, electrons go down in the same spot. We're at the same place we were before. These come and grab the hydrogen, conjugate base leaves. Again, these electrons come in and kick out water. But here's the difference. We don't have a hydrogen here. So the base goes to a next door neighbor carbon here, grabs that hydrogen and electrons go down because you can't have a positive charge on that nitrogen and keep that a stable molecule. So when that happens, then you get this double bond down here instead of up here. And you can tell the difference because this is starting with a secondary amine, and this guy starts with a primary amine. And there we go. Thank you very much.